So yeah, as Ken said, this talk is about combining free monads and free applicatives. So before we get into all of that, just to introduce myself, I'm obviously Joannidis. Feel free to add me on Twitter or LinkedIn. I work at Simple Machines, which is a consultancy doing data systems all the way from kind of engineering and DevOps through to machine learning and analytics. And if I were to describe kind of what I do in buzzword bingo, it would be big data, machine learning, and functional programming. So what we're going to cover today, I'm going to talk about abstracting effects from our domain definitions. Then we're going to look at how we can actually put these effects into free structures. And then finally, we'll look at how we can combine the free monad and the free applicative. So before we start, I know there's a lot of strong opinions on the topic of usage of the free monad. So I'm not trying to push for you to use the free monad or the free applicative over things like final tagless or whatever style you choose to use. I think they've all got a lot of strengths and weaknesses. So this talk is more in the context of what you can do if you do choose to use it. And if you're one of those people that likes following along with the actual code, I've got it up on my GitHub. So let's start with the basic domain. Let's say we have a basic user that just has a name and an age, and we have a user repository which gives us a few functions that can act on that domain. So create user, which returns a user, list users, and so on. A basic implementation in Scala, and if you're not familiar with Scala but you are with Haskell, just imagine half of that code isn't there. Looks something like this. So it's pretty common though. You might look at this and say, well, okay, this is an idealized version of what I actually want to do. I actually have to deal with failure. So you might introduce something like either, and I've put throwable here because I'm very naughty. You'd probably use some kind of proper, ADT representing all the failures in your domain. So we'll just gloss over that for now. But you'll probably also look at this and say, yeah, but I don't want to be holding up a thread. I actually am talking to a database when I'm creating or listing users. So you might also have some kind of task. And as Ben said earlier, we can turn this into an either T sort of data structure to handle our errors. Now, if we take a step back and look at where we started and where we've ended up from what we want in terms of our domain description versus what we actually have, you can see that it's gotten quite complex and there's all of this extra noise around that doesn't really tell us what our domain is doing. It's telling us the effects on our domain. So what this means is that we've actually tightly coupled our implementation effects with our domain. So you can see here either T task throwable in this case is just the implementation effects, and user is the only thing that we actually care about with our return type. So as I said, this tightly couples our implementation details to our domain, and it also means that things like testing domain logic in isolation are a lot harder. If we're talking to a database or if we're doing like future either blah, 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 and we just want to set up a use case, it's a lot harder to just test that use case directly without putting all of the extra wrappers and whatnot. So in comes final tagless, and you're probably familiar with this. It's basically just a wrapper around where we say there's some effect type. We don't know what it is yet, but we're going to say it's F. And at some point, we're going to fill in what that F is, and we're going to implement it in terms of this. So that looks pretty similar to what we started with. So it's quite a nice abstraction if you like this approach. And when we actually implement it, it looks quite similar to how we had it before. We basically just extend it, and then we choose what effect that we care about. Such as task. Now, free monad actually works quite similar to this. The main difference is that it actually reifies the domain, which means it turns it into data. So I'm basically just going to walk you through what it looks like at a high level if you're not familiar with it, and then we'll kind of get into the next part. So the first thing you do is you represent your operations as data. So we previously saw this on the last slide as the methods on that interface, this thing. So we turn that into data, and then the next thing that we do is we lift that data into a free structure. Now I'm representing the free monad with these blue boxes, and you'll see later that the free applicative is the red boxes. And then finally with the free monad, we have the ability to sequence our computation. So we can have these dependent steps by using flat maps. And what we've actually created is just a description of a program. There's no actual code that's going on here to explain how it works. It's basically just saying, I have this structure whereby the first thing that I have is data explaining create user, then the next thing is create user Sally, and then the last thing is to list users. So to make this actually useful, what we do is we interpret this structure. And we end up with something like this, where if we have a database interpreter, we'll read create user and we'll turn that into something like insert into users values John 36 into our database. Then we can do the same thing with Sally, and then we can select star to list the users. So the free monad and the free applicative both have very similar ways that you set these things up. And they roughly go encode domain as ADT, lift the domain into a free structure, write logic as a free program, create interpreters to interpret the domain instructions with some effect, and then interpret free program to produce the output effect. So starting with encoding our domain as an ADT, as we saw, it kind of looks like this, and I'm representing operations as these little yellow boxes. So in Scala, it looks something like this. We use case classes and a sealed trait to enforce this. Again, pretend that there's a quarter as much on the screen if you're into Haskell. And this F is that F that we saw before. It's the effect type. Now, Jed said naming doesn't matter, but it's very common that names do matter here, just so that you've got a little bit of context around what domain you're talking about. So this is kind of what it looks like. You've got your inputs, which previously were just the method inputs, and then you've got your output over here with some effect type, which was previously just an F of the effect type. So you can kind of see how this maps to the final tagless approach of defining your domain. Now, the next thing that we do is we lift this domain into a free structure. And this was this operation. So we're taking the yellow boxes and we're putting them in the blue boxes. And what this looks like is something like this. We have this free.liftf, and then we put the actual create user into that box. And we have the return type now of free, parameterized on user option, returning user. And we can do the same thing with the free applicative. So we can take our operations and lift them into the free applicative. And the code actually looks almost exactly the same. The only difference is that we now have free app instead of free. So a little trick that I like to use is to actually have this little wrapper that I call exec strategy, which defers whether we're going to use the free monad or the free applicative. And you can see here all we're doing is just applying that little bit that's different. And we'll see how this is useful later. So what we do is we create our repository with this exec strategy, which means that we're now returning a computation which we can choose how to lift it when we use it. Now, the next thing that we do is we write our logic as a free program. So this is creating that structure that we saw before. And this is where free monad and the free applicative actually start to come into play. So free monad is for dependent operations, i.e. sequential things. And we can enforce this with the flat maps. So in our diagram we saw, we have this flat map that allows us to say this operation happens before this operation happens before this operation, and so on. Now with applicatives, they're actually independent operations. They're not necessarily parallel operations, but we can interpret these things in parallel to make them asynchronous. So this looks something like this in Scala, and we've got this little, I think it's a spaceship operator, but yeah, pipe at pipe. And that means that this thing runs independent with this thing. So now that we've seen that, how do we combine sequential and parallel operations? What we end up with typically, when you're using free monad or free applicative, is one of these two things. Either we have a free program or we have a free applicative program. So if we want to combine these two things, we typically will have one of two choices. The first of these is to have the free applicative on the outside and the free monad on the inside. And what this leads to is a program that looks like this. So basically we have this parallel box that has a series of sequential things that run independent of one another. And within them we have operations that run one at a time. Now, this probably isn't quite as common in terms of the way you structure programs. It's more common that you would actually have a sequential program of parallel steps, which means that we put the free monad on the outside and the free applicative on the inside. So what this looks like is something like this. We have two types of steps that we tend to use. One of them is to have a single step that has no parallel operations, and the other is a single step with multiple operations that run in parallel. So if you want to have this depends on this, as you would with a free monad, there's this extra free app thing in there just to make it work on the types. And then if we want to actually run things in parallel as a program step, we now have the ability to embed them in the free applicative, which is then embedded in the free monad. So you still get that dependent ordering. Now we saw before with our exec strategy that we can lift things into either a free monad or a free applicative. So I've got this little thing that I'm writing in these slides called as program step. And all that is just a way to take either a free monad and embed it in this bigger structure, or a free applicative and embed it in this bigger structure. And for now, I've left the as program step in there just to make it very explicit about what's happening and when it's happening. So if we were to actually have a look at how one of these two is implemented, we'll take the easy one, which is the free applicative, lifting it into the structure. You can see it's just kind of being wrapped by the free monad. It looks something like this. So we're just saying free.liftf of our free applicative. The version for the free monad, you can see, needs this little red box on the inside. So it's a little bit more involved. And the code's on GitHub if you're interested in seeing how that works. But this is all kind of just boilerplate machinery that a library gets rid of. Now let's define two simple domains. Let's say we have users, and we'll say we have some analytics that we want to do on those users. I've made this just very simple, but expressive enough that it's kind of showing you that there's ways to do this with more than one domain. So with our user operations, we can create users. With our analytics, we can analyze users. So the first thing that we need to do, as before, is to lift our domains. So we have our user repository, and we lift it using our exec strategy. And then with our analytics repo, we do the same thing. Don't worry too much about all this other stuff. This inject is just to allow us to actually combine these domains later. Now, this is the interesting bit. So when we actually write our program, this is where we define the semantics of our domain in terms of sequential and parallel nature. So here we can see we have a user repository, and we want to create the user Steve, and we decide that it's a sequential operation. And then we do this .as program step to lift it into that bigger structure, the blue box with the red box inside it. And this will create a single operation. We then create Harriet, and then we do analytic steps on both of them, but we do them in parallel. So we choose to run this in parallel by calling this .par, and then combining these things to say this runs independent with this, and then we say we just want to add whatever the analytics results are together, just for simplicity for now. And then we lift this whole thing into a program step. So what this looks like is this. We end up with this create user step as a single step, then we flat map with the free monad to get the next step, then we flat map again to get the final step, and in the final step we had two things that were to run independent of one another. Now the cool thing is, without changing any of our interpreters, we can actually make our domain run in parallel instead of sequence. So we can say, I actually want to create my users in parallel now, and then I want to lift this into the program step, and then I want to analyze them in parallel. So we get something more like this. And again, this is just a structure describing what the actual program looks like. It's not doing any interpretation. So now we're saying I want to create the user Steve and Harriet independent of one another. Then I want to flat map it for dependent operations, and then I want to do analyze user 1 and 2 independent of one another. So the next thing is to create interpreters to interpret the domain instructions with some effect. We've seen that if we've got something like this where we have an operation create user and we have an interpreter, we want to spit out some kind of effectful computation. Now I've got it just to fit on the slide here as user John36, we're returning it directly, but you can imagine that this is where you do your IO and you hit the database and whatnot. So our user interpreters look something like this, at least in Scala. We have this natural transformation which takes the user operations and turns them into tasks. So remember, user operation is just a convenient name for that F, which was our effect type. So we're saying, now our effect type, we're choosing it to be a task. And then we say, given all of the different things that we have in our domain, we want to match on them, and then we want to actually implement them. So this actually is what you would typically have as your implementing subclass with any other approach. And you can do the same sort of thing with the analytics one. The only difference is that we now do it across the analytics domain. And we can obviously interpret these to different effects, but it's pretty common that they will all end up in the same program with the same effects. So it's quite common to have that. And I've put in these printlns just so that we can see when things are actually happening in a moment. So finally, we need to interpret our free program to produce an output effect. In order to do this, we need a way to combine the domains. We've seen that we can define a domain for users and define a domain for analytics, and then we can write interpreters for each one of those things independently. But putting them together requires what's called a coproduct. And you can kind of think of a coproduct very much like an either. It's basically either a user operation or an analytics operation. And it kind of ends up being this big tree. So the program interpreter is basically how we say, now we've got this big sort of tree-like structure that have combined all of our domains. How do we actually interpret something within that domain? And this program instructions is saying that that global effect type, I want to turn it into a task. And I'm going to do that by combining my slow user interpreter and my slow analytics interpreter. And this all we'll see in a second is just the way that we find where in the tree that we need to match to. So creating the program instructions looks something like this. I've added a third domain, logging, just so that you can see what it actually looks like when there's more than two. And basically this is saying, I go to the left for a user op, otherwise I go to the right, and then I've got another co-product, and then I either go to the left for an analytics operation or to the right for a logging operation. And so when we embed this in something like the free monad, it looks a bit like this. So when we get an actual operation, it'll look more like this. We have an analytics operation, and then we have a user operation, and we've got this kind of nesting of these either co-product types. And then we can say, I want to do an analytics operation, flat map it, and then do a user operation. And that enforces that dependent sequence of steps. So when we actually interpret it, that OR that I told you about before, that's basically just a way to combine our interpreters such that they'll always find the correct thing in the hierarchy. And this is all type safe, so it won't compile unless you actually do it in the correct order. So in this case, we have an analytics operation in this structure, and we interpret it with the analytics interpreter. Then on the other hand, we have a user operation, and we interpret it with the user interpreter. But we saw before that when we're combining this sequential and parallel execution, we actually have this extra layer, which is the free applicative. And we've then got this embedded structure. So we have a way to turn that structure into an effect, but we don't have a way to turn the red part into an effect. So we might have something like this. And we don't actually have a way to say that our interpreter can read this thing, because it can only read the inner side, and you're still ending up with this free and free applicative stuff not resolved. So in order to make it parallel, we add something like this, just a little parallel wrapper. And what this basically does is it says, give me some program instructions and something, in this case it's a task, that we can evaluate it to, and some applicative instance G. Now the reason we have this applicative is so that we can show that these things are independent. And then we extend free app of program instructions to G. And that's basically saying now we can transform the red thing with the operations within it into some effect type. And that's basically just the implementation. Don't need to worry too much about it. So when we actually run the program, it looks like this. We say we have our program. We want to use our program instructions, which was that co-product we defined. And then we want to fold map with our parallel interpreter. And the parallel interpreter is what allows us to run these things in parallel. And then we do unsafe perform sync, because we're using a task in this case. So if we take a look at the program again, what we saw before, we had create users in sequence and then analyze them in parallel. And when we run that, we actually get exactly what we expect. We create the user Steve, then we finish creating the user Steve. Then we create the user Harriet and finish creating the user Harriet. So those things happen in sequence. And then you see we start analyzing the user Harriet and then start analyzing the user Steve, and then they both finish. So that's them running in parallel like we expected. And with program 2, we have the same sort of thing that we'd expect. So we said we want to create the users in parallel, and then we want to run the analytics in parallel as two dependent stages. And you can see here we create the user Harriet and Steve, and then they both finish. Then we analyze the user Harriet and Steve, and then they both finish. So things to note. The target effect must have an applicative instance. The reason for this is that you actually need to evaluate these things in terms of the free applicative. So whatever you end up using, task is an example that actually does have one. The task in Scala Z, this actually kind of bit me when I first wrote this. I ran it and the whole thing seemed like it was running in sequence. In Scala Z, because you have the top level monad and it brings in the applicative, it's actually a sequential applicative, which was a design decision. But there is another one that's tagged as at parallel, or you can implement your own if you prefer. And the other thing, as I mentioned, the at as programmed step, you can remove most of that boilerplate with implicits if you really want. I just left it in there so you can kind of see where it's lifting into that bigger structure. Now, there's obviously a lot of boilerplate. You probably think, Jesus, why would I ever use this? There is libraries that actually abstract out a lot of this boilerplate with macros, so it ends up looking more or less exactly like the free final tagless. And this kind of gives you a lot more expressive power. Now, I personally think if you don't need the expressive power, this is probably a bit overkill. But there are certainly applications where this kind of thing is really nice, especially with sort of compilers and stuff. And Freestyle actually defaults to this structure that we saw, which is free on the outside, free applicative on the inside. And there are several integrations and library abstractions out of the box, which is really nice. So it means that you don't have to write your interpreters for a whole bunch of different things. They're all just there, as if a standard library would be. And the other thing that it does that's really nice is it has out-of-the-box optimizations to reduce the overhead of using lots of domain algebras. So we saw it with two. We saw it with users and analytics, and then we saw it with logging. And you can imagine that your application might be split up into 50 or 100 of these things. And you're kind of building up this massive tree in that case. And that can actually start to be a bit of a performance issue. So it has this underlying library called IOTA, which implements the coproducts as a linked list at the type level. And that means that you have much faster access when these things scale. So just to recap what we've covered, we looked at why we abstract effects from our domain. We looked at actually abstracting these effects with things like final tagless or free structures. We then looked at combining free and free applicative to introduce parallelism into our domain without having to re-implement our interpreters. And then finally, we looked at Freestyle to remove boilerplate. Thank you.